Okay, this is the second hour of Physics 1C for November 17th. We're now going to move on to talking about capacitors and how they operate in AC circuits. And then we'll put kind of everything together. Okay, so just as before, we'll start off with the circuit. We've got our AC source connected up now to a capacitor with a capacitance C. And at a moment in time, we'll say that the current that's flowing in our system we call I, again, where I as a function of time is given by a cosine function. Now, for this one, to investigate it, we kind of want to think about what's happening here. So if we kind of try to just visualize what's going to be happening, this voltage source is going to be applying current to the left and then right, left, right, left, right. And the effect of that is going to be that the left side of the capacitor plate may be positive at one point in time, then it'll drop to 0, and then it'll be negative, and then positive, and then negative, positive, negative. So while the current's flowing left and right, the polarization of the capacitor is going to be oscillating. It's going to be positive, negative, negative, positive. It's going to basically be positive at one point in time, and then it'll be negative at another point in time, just depending on what direction the current's flowing. And if we want to kind of just understand big picture what we're going to kind of get out of this, we can say that the capacitor has the effect of kind of always applying a voltage that is opposite to the voltage of the source, in a way, or at least out of phase with it, just like we saw with the inductor. And that's because when the current pushes in one way, the capacitor kind of acts like a spring and tries to push the current back in the other way. All right, so to analyze this mathematically, we'll say, okay, current, that's really the time rate of change of charge. And if we want to rewrite that kind of like this, we could say that dq would be equal to I times the cosine of omega t dt. And then what we could do is we could integrate both sides of this. And on the left-hand side, we would get the charge as a function of time. And on the right-hand side, well, if we're integrating cosine of omega t, then what we're going to get is I divided by omega, and the integral of cosine would be sine. And then, in order to get what we'd really like out of this, what we really want is to get the voltage as a function of time. And if we know what the charge on the capacitor is, then the voltage as a function of time is equal to the charge on the capacitor divided by the capacitance. Now, we should be clear what we're talking about here. Q would probably be the charge on one plate. So if this one was positive Q and this one's negative Q, we're just talking about the charge on the left plate here. All right, so all we really need to do here to get the voltage across the capacitor then, as a function of time, is to just divide by C. So we would have I over omega C, and that's equal to the sine of omega times T. Okay, so now we look at this piece and say, well, that must be the voltage across the capacitor, kind of the maximum voltage across the capacitor. So we rewrite this as Vc of T is equal to big Vc times sine omega T. We need to do something with this too. I realize we got to shift it. But now our Vc is going to be equal to I divided by omega c. Come back to this. All right, what's sine? Well, the sine function here, we can use another identity. We can say that the sine of theta is equal to the cosine of theta minus pi over 2, I think. Sound like right to y'all? Sounds right to me, just thinking about the functions themselves. Just looking at my notes to make sure I'm right. Yeah, cosine theta minus. So we would write this then as the voltage as a function of time would be equal to Vc times cosine of omega t minus pi over 2. And what that means is that if I compare this, now the whole goal is to compare this back to the current, right? maybe it's not obvious why we keep doing this, why we keep comparing it back to the current, but it will become obvious in the next, when we put everything together, I hope. But I cosine omega t and cosine omega t minus pi, what this tells us is that the voltage across the capacitor lags behind the current in the system by 90 degrees. And the kind of mnemonic for this is ICE, which is where current now leads voltage, or leads the EMF, whatever you want to call it. So you've got ICE for this one. You've got Eli for this one. Where was it? Eli, right here. So the whole thing is Eli the ice monster, which is definitely very juvenile, but it's still easy to remember. I mean, I still remember it, so it's nice having little things like that. Okay, so if we want to draw a phasor diagram for this now, so our phasor diagram now is going to have our current. Again, we'll just put the current in the first quadrant. We don't have to do this, but it's a good way to be consistent. Okay, so that's my current phasor. It spins around in a circle. It always makes this angle of omega t right here. And then we drop in another phasor for our capacitor. And according to this equation here, the voltage across the capacitor needs to be behind this by 90 degrees. So we drop another, oh, that's too bad. Okay. We drop another line this way. We need to get this one to 90 degrees, so we'll just manipulate it a little bit till it looks close to 90. Probably a little bit more. That's more than 90. That's like right about 90, I guess. Okay, and so then our angle now that's made with the x-axis for this one right here, so that's a right angle, which means that this angle here would be omega t minus pi over 2. And again, the way we figure out the voltage at a moment in time is we just drop a little line like that, and that's going to be my voltage at a moment in time, Vc. Oh, and the length of this one is going to be V, big Vc. And then, of course, we do the same thing with our current again. And our current phasor would line right up here. And that's going to be the current. Kind of running out of space, but that's current I. And again, these phasors, they rotate around in a circle, right? And there we go. Anyone have any questions? I think the way that I drew this, it's kind of backwards, right? Probably should have drawn it this way, because we measure angles like that, right? For omega t minus pi over 2. There we go. Anyone have any questions? All right, let's go back to this piece. So now what we're going to do is we're going to say, so since Vc, I thought I switched colors there. Okay, since the voltage across our capacitor is equal to I divided by omega c, what we're going to do is we're going to take that 1 over omega c thing, and we're going to define it as what we call capacitive reactance. So what we'll do is we'll say, let xc be equal to 1 over omega c. Then we can define the voltage across our capacitor as being given by I times xc, where xc is given like this. The units of this are ohms again, and we can figure that out if we kind of work out the units down here of 1 over omega c, which you would get, but you get ohms again. All right. And so this tells us what a capacitor does in an AC circuit. It says, if you tell me what the voltage is, I can tell you what the current is going to be, and the current is going to be inversely proportional to the inductive capacitance. Sorry, the capacitive reactance. That's the name of this. This thing is called capacitive reactance. You could just call it reactance if you want to. Reactance. Just call it reactance if you want to. But then if we kind of think about what this looks like over here, because it shows up in the denominator, the way it would look would be omega c times Vc, right? So what's going to happen here? If the current, if omega is big, what does that mean about the output current? If the frequency of the oscillation of the source is big, what does that mean about the output current? Current's large, yep. And if omega is small, that leads to current is small. So the capacitor can be used to produce something that's called a high-pass filter. And that means it lets through the really high-pitched sounds. Okay? Any questions about that? Remember this definition here. These two are important. All the other stuff is just theory. And then, of course, you got to remember this stuff, too. Why would that be the case, by the way? So we had an understanding with inductors that high frequency, it makes sense that you get small current, because high frequency is exactly what an inductor is designed to resist. Why would it be that the capacitor has the effect of not being nearly, like, think about it this way, the capacitor kind of does less when omega is big, but it does more when omega is small? Why would that be the case? Think about what a capacitor is. Why would it be the case that when the frequency is big, the current's big? It's almost like a way of saying that when the frequency is big, the capacitor acts like a resistor that has really low resistance, right? Why is that? Why would the capacitor do more when the frequency is small than it does when the frequency is big? Yeah, that's right. Mr. Miara says, too much charge builds up on the capacitor plates if the frequency is small since it allows more time. Yeah, exactly. The longer that it takes for the current to switch directions, the more time the capacitor has to build up its charge, and that's when the capacitor really does something, is when it has, as much of a charge as it can handle, and it's exerting this kind of opposite EMF. Yeah. Yes, that's pretty much it. High frequency, and the plates barely ever even charge up. And that means that, the capacitor doesn't do as much. So, if you think about this, this is something that's really unique about AC circuits, is that in a DC circuit, what a capacitor does is it basically just holds charge for you, right? But in an AC circuit, it basically just kind of acts as this kind of rebound point for the current in the circuit. And if you let it charge up too much, then it's actually going to produce a resistance to that current, right? Because if the current's flowing this direction and there's a bunch of charge on the plate, it's not going to have an easy time pushing more charges on that plate, right? Because that's what the capacitor basically does. So while a capacitor can block DC current, it doesn't block low frequency AC current at all. It, in a way, it almost enhances it. Okay, there's our three things. So I just want to kind of summarize here. Resistor, I and V are in phase, right? Inductor, the voltage across the inductor leads the current by 90 degrees. Capacitor, the current leads the voltage by 90 degrees, exactly the opposite of the inductor. So if we summarize all of those, there's a little table over here that we can use. I could probably write all this stuff out, but maybe it would be more informative if I did it that way, but this is a summary. Okay, really cut. That's a summary of everything that we just said. We've got our circuit element, so the resistor, amplitude relationship, Ohm's law, V equal to IR, circuit quantity, resistor, R, phase of voltage, in phase with the current. Inductor, VL is equal to IXL. This is the inductive reactance. XL is defined as omega times L, and in this case, the phase of the voltage is that it leads the current by 90 degrees. In the case of the capacitor, it's V equal to I times XC. XC is 1 over omega C, and the phase of the voltage is that it lags the current by 90 degrees. It's kind of a little summary of all the things that we just discussed. Okay, so the next thing to do is just put them all together. And this is where we get to the point where we can actually start doing problems, which is nice. So that's going to be looking at an Lrc circuit. A lot of acronyms there. Hopefully you all know what they mean at this point. Inductor, resistor, capacitor, alternating current circuit, right? So to get this, what we need is, we need an AC source, right? That's that. And then we just need to connect them all up. So we've got inductor, resistor, capacitor. Oh, I should say this is a series circuit. I think most of the problems that you're going to see are with series circuits. There are some parallel circuit problems in the textbook, though, if you want to look, or in the, there might be one or two in the textbook, but I know there's some in the lab manual if you're interested in doing some more problems with these. So we want to know how this behaves, and in order to do that, we're really going to need to define some things that we're going to be measuring here. Okay, so what we're going to do is we're going to say, suppose that we attach up right here something, and this device is going to be like a device that's going to measure the inductance across, the voltage across the inductor VL, and then we set up a device across our resistor, and it's going to measure the voltage across the resistor as a function of time, and then we set up something to measure the same thing across the capacitor. It's going to be voltage across the capacitor as a function of time, and in addition to this, we're also going to want to measure the voltage across our source as a function of time, and that's what we're going to call Vs. So Vs will be the voltage of the source. As a function of time. All right. And we're going to assume that our current in our system right here is once again we're just gonna start as that. That's going to kind of be the base point that we compare everything to. So we already know how the voltage of the inductor, the resistor, and the capacitor compare to the current, and so that's going to be the biggest thing that we want to look at. All right, so how do we do this? This is where our phase diagram is infinitely useful. Okay, now something to think about, a question to ask yourself, I guess, before we go through this is, if I think about what the voltage across the capacitor is, plus the voltage across the resistor, plus the voltage across the inductor, the question would be, is this equal to the voltage across the source? So I write an equal sign with a little question mark above it. Is this true? Is it going to be the case that the voltage across the conductor and plus the voltage across the resistor, plus the if I look at the readout of this one, I look at the readout of this one, I look at the readout of this one, is it going to add up to this? Like if this was 1 volt, this was 3 volts, and this was 7 volts, would it be 7 plus 3 plus 1, so I get 11 volts here? Just something to think about. We don't have to answer it right now. We will get an answer for it, but you should think for yourself what you think the answer to that question is. Okay. So, the next thing we're going to do, this is where the phasors are really nice. If they seemed confusing to you before, hopefully when you see the value of what they can do for us, you'll be convinced somehow that it is something that is useful. Because it saves us from having to do a whole lot of trig identities. That's basically what it does. All right, so the way that I'm going to do this is going to be kind of simplistic. I might try to draw a more complicated version. Nah, we might as well. We'll do the normal version, I guess. I don't know. I don't want to make this too complicated for you. But since we're doing it on a computer, we can fix any mistakes we make, so that's fine. All right, so let's start off with our current. Let's use red for the current. Or we'll use green for the current. Shapes, this one. And let's say our current looks like this at a point in time. I'm going to have to make let's just make this bigger. Just want it to be wider, maybe a little bit taller. Okay, and this one, this is going to be my current phasor. Okay, so that is going to have a length I, and it's going to make an angle omega t right here. I don't know that I'm going to be able to draw the angle for every one of these, but we'll try. Now, the next thing that we're going to draw is the voltage for the resistor. If I want to draw a phasor that's going to represent the voltage across my resistor, what is it going to look like? And where would I draw it? Do I draw it at right angles to this? Do I draw it at 180 degrees away? Do I draw it right along the same line? How do I draw the phasor for the voltage across the resistor? What do we know about the voltage across the resistor? It's along the line, right? Because this was in phase with I. I should write it like not big I, but little I. Because little i's are the current actually in the system. Okay, so that means we'll use, I guess we use red for all the voltages. So, red. Not that one, this one. Okay, so then we draw an arrow like this. And we'll just make it like that. Kind of about the same length, but not exactly. And maybe I'll just shift it up a little bit so you can still see the green line below it, but yeah, that's VR. Okay, now what about the voltage across the inductor? How should it be drawn? Should it be drawn 90 degrees ahead or 90 degrees behind? And I scroll back up here so you can kind of see. Where should the voltage across the... Yeah, voltage leads the current, right? So that means that when I draw in my phasor for VL right here, then, I don't know, it's going to take the shape away because I just did it, right? Okay. So VL is going to go this way. It needs to be 90 degrees ahead, not only of the current, but also the voltage across the resistor, right? Because the voltage across the resistor is automatically in phase. So this is going to be at a 90-degree angle to both of them. That seems fine to me. And that's going to be the voltage across the inductor. All right. So one more. We need to do the voltage across the capacitor, and we know that that one is the one that's going to lag I by 90. So it's going to be going down into the third quadrant, or fourth quadrant. This one we're going to intentionally draw a little bit shorter for reasons that will become apparent very quickly. So there we go. That is VC. And now the idea here would be that all of these phasors basically stay locked just as they are, where, you know, these two make right angles here and these two make right angles here, right? I'm going to take those off the diagram, but they stay locked like this and they rotate around in a circle like this. At any moment in time, I can drop a line down like this, and I can figure out exactly what the voltage across the capacitor is going to be. And I realized something about my notation here that I need to fix, actually. It's the length of these things. I didn't quite do that right. This should be big VR. And this should be big VL. The length of these is kind of the maximum value. It's the the projection along the x-axis is what the individual currents are going to be, or the individual voltages are going to be. Right? So if I want to find, for example, what my voltage across my inductor is, I have to drop a line down like this, and then a vector that looks like this would be VL. Same thing for VC. We draw a line like this and go like this, and that would be VC at a moment in time. Okay? I'm going to get these off the picture for now, but that's just, in general, what goes on there. You will notice, by the way, that in this particular scenario, VC looks like it's positive, right? While VL looks like it's negative. Can everyone see that? VC is positive, and VL is negative. Right? Okay. Getting rid of those lines now, because now what we want to do is we want to kind of put all of these things together. Now, we have phasors, but they're similar to vectors in the following sense. What I can do is I can take VC right here, and I'd actually like to change the color of VC just for the purposes of what we're trying to do. So let's do that. Let's make VC a blue color. Oh my god. Let's make VC a blue color. Okay. And then what we're going to do is we're going to copy it and paste it, and we're going to do it like this. Oh, look. It sure looks like they're along a line, doesn't it? But I guess they're not. Do like that. Let's try that again. As soon as I copy paste it, you can see that they're not linear with each other. It's really off. Okay, we're just going to ignore that for a second. I'll get them more lined up here. What I'm going to do is I'm going to basically add these vectors tip to tail like this, okay? And what I'm going to get out of that is a new vector. And that vector is going to be, or it's going to have a length that's going to be VL minus VC. That's the shorter one right here. Does that make sense? They're both along a line, right? So the way you add vectors that are in a line, you just kind of put them tip to tail. And we get this VL minus VC here. I'll stop for a second. Is that confusing to anyone? Does anyone have any questions? Everyone following along? Is everybody lost? How are you doing? Alrighty. So, now what we're going to do is we know that if I have VR pointing this way, and if I have VL and VC pointing this way, I can add those two vectors together, right? They're phasors, but phasors are a type of vector that just spins. So what I can do is I can come in here, and if I draw a line... Well, I'll tell you what we need to do, actually. No, I don't want to. We're going to kind of eyeball it. It'll be fine that way. So now if I draw a vector that goes like this... Now, this vector needs to be a very specific length if I want to do it properly. I won't be exact, but I'll do my best. So it needs to have an x component like this, and a y component like this. So it needs to kind of go like this to kind of complete a parallelogram here. And we're going to kind of roughly say that's about right. This be a little bit longer. It's probably too high. I think that's pretty good. And this is going to be Vs. This is going to be the voltage we measure across the source. And it's going to have a component on this side. Here, let me undo that. Let me move. Let's move VR below this so we can actually write this the way we want to. Come on, let me just click, please. There we go. There we go. Okay. So now, this side over here has a length that's VL minus VC. And the side on the bottom is VR. And you have that side that is VS. We're going to define this angle right here on the inside. We're going to call it phi. Okay. And phi is going to be the phase difference between V source and VR. All right? And now we can kind of start making some statements. We can start doing some mathematics to simplify everything. We can say that the size of VS, if we were to square it, should be equal to VR squared plus, I'm just adding two vectors, Ash, VR, and I'm adding this vector VL minus VC. That's why I drew it over here like this as well. So say we're adding this vector and this vector here. Tip to tail, exactly. We're just going back to like the early definitions of how we define vector addition. All right, VL minus VC. Yeah, see your 2A teacher that told you, like when you're taking 2A and they told you about how important it was to understand vectors and the tip to tail method, and then you only use the tip to tail method that day, and then maybe you use it at the beginning of 1A. We get to use it again right here at the end of Physics 1C. We're using tip to tail method again, which is, it's nice seeing things show up again. Okay, so we get that relationship right there. However, we also know some things. I'm going to scroll up a little bit here because we have them all written down in that table. We know that VL is actually just equal to I times XL. And we know that VC is just equal to I times XC, and likewise VR is equal to I times R. So let's plug those in. So what we'll have is VS is going to be equal to the square root of, this is going to be IR squared. So I squared R squared. Plus VL is going to be I times XL minus VC, which is I times XC. These are all squared. Every single one of these terms has an I in it, which we can factor out. So we end up getting VS is equal to I, because they're squared inside of here, so when we factor them out and pull them out of the square root, we get I times R squared plus XL minus XC squared square root. And all of a sudden, we have a relationship that once again looks really like Ohm's law. It's VS is equal to I times a whole bunch of stuff. And I mean, whatever this stuff is equal to, at the end of the day, it's just something that's measured in ohms, right? Because resistance is measured in ohms, XL is measured in ohms, XC is measured in ohms. You take the square root of it, you get ohms, right? So really, you just have this whole new thing here that, in a way, basically describes the entire circuit somehow. And it shows up as resistance squared plus the difference between the two reactances squared, and XC shows up as negative. And that's largely because of the fact that VC was lagging behind the current and VL was ahead of it. That's where the positive and negatives kind of come in here. So what we're going to do is we're going to define impedance, Z, or Z, however you pronounce it, is equal to R squared plus XL minus XC whole squared, square root. And then we get this new expression that the voltage measured across our source ends up being equal to the current flowing in the system multiplied by the impedance. So Z is impedance. And if you think about it, impedance is kind of another way of saying resistance, right? Because the way that this ends up working out here is that the bigger the value of Z, the smaller the value of current is going to be, right? I mean, we can write this also as, if I take the voltage across the source, this in America, this would be like 170 volts, we said, right? And then I divide by Z, that's going to give me my current. So the larger Z is, the smaller the current is. The bigger Z is, small Z, big current, big Z, small current, right? So it acts just like resistance. This is kind of like the alternating current version of resistance. Impedance is. And it can be calculated just as long as you know what resistance, XL and XC are, keeping in mind that XL and XC are functions of frequency, right? They're functions of the frequency. We could say a lot more about this, and we're going to do so, but I'm going to stop there for a second in case anyone has any questions. Okay, so a couple other things I want to mention here. I mentioned that there's this angle phi right here, and you could ask, okay, well, what's phi equal to? And we can say pretty exactly. Now, we can say, if I write the tangent of phi, the tangent of phi would be equal to VL minus VC over this side, which is VR. But VL is IXL minus IXC divided by VR, which is IR, according to Ohm's law. All these currents cancel, right? And what we get is that tan phi is going to be equal to XL minus XC divided by R. Phi is what we call the phase angle. For the whole system. It's the phase angle between the current and the voltage for the whole system. And once we know what the phase angle is, we can actually make the following statement. The voltage across our source as a function of time now is going to be equal to Vs, which is Iz, but I'll just write it as big Vs, multiplied by, and again, this would be like 120 volts in the United States, multiplied by a cosine function. But in this cosine function, we can now add the phase angle. Because after all, the voltage phasor is now exactly phi degrees ahead of the current phasor, which lines up with the resistance phasor. So phi tells us the phase angle. Now you can imagine a system in which phi was 0, right? What would you have to have happen for phi to be 0? Here's the definition of phi right here. What has to happen for phi to be 0? Resistance could be really big, but let's ignore that. How else could phi be 0? XL minus XC would need to be 0. That's exactly right. As long as the numerator up here was 0, then you would get tan phi equal to 0, and the arctangent of 0 is 0. So if XL is equal to XC, that special case, then you get phi equal to 0. All right. What else can we say? We can write down what the cosine of the angle is. As we will see, that's going to be something that's going to be important. It's going to show up in your homework. So cosine of the angle, phi. For this one, we would say, okay, cosine is going to be this side, which is Vs, divided by this side, which is VR. Why does this seem backwards? That's not right. That's not how the cosine works. That's not how the cosine works at all. Sorry about that. The cosine of an angle is the adjacent, which is VR, divided by Vz, right? Does that look more like a cosine function to y'all? VR is IR, Vz is Iz, so this is just equal to R over Z. And R over Z is cosine phi. We're going to learn that this has a special name. Well, I'll just tell you what it is right now. It's called the power factor. It's called the power factor. It's part of the reason why is because it's going to show up in our equation that describes the power of this. But you can kind of understand what it is in the following sense. The maximum value of cosine is 1, right? That occurs explicitly when r is equal to z. And if you think about it, the only time that r is equal to z, what does that mean? That means that this term, xl minus xc, is 0 again, right? So it happens to be the case that if you have these perfect values of your inductance, capacitance, and your angular frequency, then you can get it so that the voltage of the source and the voltage of the resistor are in phase with each other, that the voltage and the current are basically in phase with each other. And the reason why this is related to power is because if the voltage, which is effectively kind of how hard the source is pushing on the electrons, right? And the current, which is how fast the electrons move, if the force on the electrons and the direction they're moving are always in phase with each other, right? That means that your system is basically outputting all the possible power that it could without any of it being kind of sucked up by the fact that there's a kind of lag between the motion of the charges and the applied force on the charges. This is like a driven oscillating system. It's a driven oscillating system. The best thing to compare it to, as I said earlier, is pushing someone on a swing. If you have a child that's being pushed on a swing, so you're over here, you're pushing, okay? This is, you're the source. you're the voltage source, the source of the EMF, right? The EMF is the force, right? You're pushing the child swings this way, the child swings that way, right? The way in which you can get the most kind of power efficiency out of this system would be to make sure that every time the child is moving to the left, you push to the left. And every time the child is moving to the right, you push to the right. That would be a in-phase system where the force is in phase with the velocity. Does that make sense? The force is in phase with the velocity. And how does that show up? Well, power in Newtonian mechanics is force times velocity times the cosine of the angle between the two of them. And when they're always in phase with each other, this term is 1, and you just get power equal to force times velocity, right? So can you kind of see why we call it the power factor? If you're pushing the child to the left and the child's moving to the right, you're going to sap energy from the system. Does that make sense? The child's coming towards you and you push the child in the same direction, the child's going to slow down, right? But if you always push in the same direction as the child's moving, then you're going to get kind of an amplification of the power in the system, right? Did I go through that too quickly? Does it make sense? We call this a driven oscillation. We call this driven oscillation. Normal oscillation is just where you freely let the child swing back and forth, right? That's what a pendulum does. That's what a mass on a spring does. That's what, yeah. They just kind of swing back and forth. But you can keep putting energy into the system, and you can make it so that the amplitude at which this person's swinging gets bigger and bigger by driving the oscillation. Okay. Does that all make sense? Does anyone have any questions? The things that are... Go ahead, Mr. Meowers. I'll wait. I always have this problem of talking immediately as soon as I ask if you have questions. How is power factor useful in a problem? Well, I mean, I know one of your... that's a really weird question, I must say. I'm not trying to be rude or anything, but I know one of your problems, it's going to give you the power factor. It is like efficiency, exactly. It's more like an efficiency type value, exactly. That's why it's called power factors, because it's related to efficiency. Any other questions before we move on? I think we can do a problem now. I think I covered everything. Oh, one other thing to say here is this equation, Vs equal to Iz, even if you talk about RMS values, you get the exact same equation. So if you do VRMS, that's going to be equal to IRMS times Z as well. You get the exact same equation. It doesn't really matter which one you choose. That's not going to be true for everything, but this one it works because to get the RMS current, you just divide the left and the right-hand side of the equation by square root 2, and immediately kind of gives you this one here. Same thing can be said for this equation. We could do the RMS on both sides if we want to as well. No, that's not true. Not for this one, but... well, let's do a problem. It's 7:50, so I guess it kind of makes sense to take a break now. But what I want to kind of do is probably just put this problem up here so you can see it. It really has two parts. Where's the other one? Oh, it's right here. So what we'll do is we'll put these two parts, and I'm going to pull this one down here too. Wait, did it just pick up the one below too? Oh, no, it didn't. Okay, cut. Go to the left. Paste these down here. Okay, first of all, let's kind of look at this picture real quick for a second here, and I'll probably leave this one up while we go to break, and I'll leave the problems up too. So just pull these things together here. There's two speakers connected in a loudspeaker system, and then a problem that we're going to do here. And I'll kind of like allow you to take some time to read these over during the break, and that way when we come back we can maybe just have you do the problems, because that would be pretty valuable. Okay, so this is kind of a diagram of a speaker. I don't know how accurate this is. Those of you that have spent some kind of time dealing with systems like this probably know better, but what they're trying to say is that you've got some amplifier over here, you've got a tweeter, and you've got a woofer. And the goal of the woofer is to get really deep bass sounds, and the goal of the tweeter is to get really high frequency sounds. And when we combine those together, you get music. And if you look at the way that the circuit's connected, the circuit that has the tweeter in it basically is a capacitor connected with a resistor and then back to the source. And then connected in parallel to that is the circuit that's connected to the woofer, and it has the inductor connected to the resistor connected back like this, right? And so the idea would be, of course, that the inductor is the thing that allows through the low frequency sounds for the woofer to get the bass sounds, and the capacitor is the thing that allows through the high frequency sounds to get the kind of soprano or treble sounds. Right? Anyway, so what we want to do is use the kind of knowledge that we just learned to solve this problem right here. Solve both of these two are connected to each other. But the idea is we're going to have a series circuit. The figure is this figure here that's connected in series, and we have a resistance of 300 ohms, an inductance of 60 millihenries, a capacitance of 0.5 microfarads. This is going to be our maximum voltage in the system, 50 volts, and then the angular frequency is 10,000 radians per second. We want to find the reactances XL and XC, the impedance Z, the current amplitude I, the phase angle phi, and the voltage amplitude across each circuit element. On the left, aren't these in parallel? These are not connected to each other. Sorry, no, it's a different figure. It's the figure for this. I just put this up so you guys can look at it while we're on break. But the figure for this circuit is just going to be your normal capacitor, inductor, resistor, RLC, all connected up in parallel to, or in series with a voltage source like this. That's our picture. That's what 31.13a looks like. Okay. Yeah, so we want to basically just kind of calculate all the things that we just discussed here. So what I'll do, we'll take a break, maybe a little bit longer. We'll take a 12-minute break. We'll start again at, what is that going to be? 7:15? No. 8:10. No, that's a 17-minute break. 8:05. We'll start at 8:05. When we come back, I'm probably going to have y'all solve most of these things. I might kind of guide you and have you kind of work on it and solve them. So if you want to get started now, you can, but you can also take a break. I'll be back. us continue. Okay, so we're talking about an Lrc series circuit. We're going to be doing both of these problems. I guess what we'll do is we'll just leave some space and we'll do this one afterwards. Once we've done this one, the second one's pretty easy anyway. But it is relevant to look at just for some of the reasons that we discussed a moment ago. All right, so Lrc series circuit. In the series circuit of this figure over here, we've given... Oh, I need to start recording. Wait, have I been recording for over an hour?